In this video, I'll be looking at the concept of SLAM, or simultaneous localization and mapping. This is an important field, particularly when we're using mobile robots in the exploratory area where we don't know the environment around us, trying to create a map at the same time as actually navigating ourselves around. So think about it this way. Imagine you're an explorer on another planet or the moon. You don't have a GPS, it's the moon after all, but you can imagine these sort of things a couple of hundred years ago before we had some of this modern equipment associated with it. You don't have a map, you're the first one there, and you're making a map as you go. The idea is it's your job to create an accurate map of your environment as you explore, as many of our explorers did a few hundred years ago, and you need to know your position within the map at all times. So you need to know where you are so you can return to base if you need to. For example, if you need to get food or supplies and things like that. So this is a bit like the SLAM problem for mobile exploratory robots, where they're creating this map and working their way around, and they know how to get back to base if need be, if they need to address something or explore something. Essentially, this is the problem that we call SLAM, simultaneous localization and mapping. So this was formulated by Durant White and Leonard, and there's been a whole series of papers and research done in this particular area. Essentially, the robot's tasked with creating a map and localizing itself within that map. So localization and mapping going on at the same time, which is where it gets its name from. It's been one of the significant recent problems related to research in mobile robotics. And it's more recently, in the last decade or so, that there's been some really good solutions that have been employed to make this work and make it work effectively and well. So there's some important questions that we need to ask in robot navigation, and these are ones from one of Durant White's early SLAM papers. He says robots need to ask these questions: where am I, where do I want to go, and how do I get there? And essentially the first SLAM question that we're asking is, where am I on the map? A robot needs to know where it is, and it needs to know where it is in this case with respect to the map that it's actually creating. Where is it in here? For example, if we're thinking about these mapping sort of things, if you're trying to get to my office, it's not going to do you much good if I just give you a GPS coordinate. GPS won't work indoors anyway. But if you had a map, you'd be able to actually see where it is and localize yourself within that map and see where you're going. You can't just walk straight to my office from the road. You need to walk through doorways and walk upstairs and so on and so forth. So unless the robot knows where it is on the map, some of our other questions related to where do I want to go and how do I get there become quite difficult, because it can see those from the map as well. So why is SLAM a difficult problem? Well, firstly, we have odometry errors. So we looked earlier on in the course at sort of errors that we have with odometry and increasing error over time. We also have errors in robot perception. So the robot will be sensing its environment and see obstacles and things, but there'll be errors associated with that. And we've talked about those errors and how we can mitigate some of them. The next part is, though, this robot's in an unknown environment, and it doesn't actually have a map of the environment. It's actually creating that map of the environment, and we want it to be an accurate map of the environment. And one thing that's quite difficult is recognizing a path that's been previously traveled, because sensors will be approaching and will have a different view each time the robot goes around and loops back to a position. They'll be rendering in a different way. We need to try and recognize that, oh, have we reached the same point again? And particularly for maybe an office environment where it's very regular, we've got doors that space a certain amount of distance apart and things like that. We don't want to think that we've looped back to the same spot several times when we actually haven't. We've just found another part of the corridor that looks similar to the one that we previously assessed. We also have an incomplete map. So the map's being built up and it's incomplete and potentially changing. So landmarks might be moved, things within the map will actually change over time. It's a dynamic environment after all. So there's a number of different types of SLAM. We'll be looking mainly at EKF SLAM, extended Kelman filter SLAM, but we also have fast SLAM as another technique which tries to simplify some of the computation involved in there. So what about the SLAM hardware? Well, we'll assume firstly our robot has fairly accurate odometry associated with it. And so in the short term and in smooth surfaces and things where it's running well, we'll be running reasonably accurately with the odometry. And we'll have a 2D LiDAR. So the older systems where SLAM was starting out use sonar, but this isn't very fast and it's very inaccurate compared to the LiDAR systems that we're using. Of course, there's a significant increase in cost as well. So this is the sort of hardware that we've got associated with it. And first we'll look at SLAM diagrammatically. So what's actually happening? We have our robot there, which is our triangle. We have our rangefinders sending out pings and sensing the distance to various obstacles and landmarks. And then we have our landmarks, which are our stars that are there. So the robot will initially measure all the landmarks that it can actually see and measure the distance from itself to each of those landmarks using whatever sensors it's using, probably the laser rangefinders that we had there. And then it will move. And based on the odometry that it's got, it will estimate its new position based on how it's moved. And it will be doing this in real time. And so it's moved from that initial position, and we've got that line there, the dotted line, or the dashed line, that's indicating the odometry estimate of its new position. And then we use our laser rangefinders again to measure our landmarks. And we'll find they probably don't quite match up to where the robot thinks it is. So what we'll be doing is saying, we probably trust our sensors more than we trust our odometry because of all the errors and accumulated errors and things that we have related to its odometry. So that we'll use its sensors to estimate its new position within the environment based on where it can see those landmarks actually occurring. Now, rangefinders aren't perfect either, neither is odometry. So the real position where the robot is probably somewhere in between the two, probably a bit closer to the rangefinder position rather than the odometry position. And so we can see that in this diagram here, where we have our 3 landmarks there, we have our odometry estimation, we have our sensor estimation, and then we have our actual position, which is quite close to the sensor estimation, but it's not quite there. We should actually call that a pose because we're really not just interested in the position, but the orientation of the robot as well within the environment. So why do we do odometry in the first place though? Well, although it's fairly inaccurate, particularly over long periods of time where we get accumulated errors, it'll give a pretty good approximation where the robot's actually moved to over short periods of time. So it gives a pretty decent initial guess and helps localize the robot within its environment. So that will help it make it easy to correlate the landmarks. We're not trying to guess where the robot is based on the whole map, and we could have moved in any direction, any amount of distance, and trying to localize ourselves. We've really moved a short distance. We know what sort of direction it's in, and we'll get us approximately there. And so it will basically generate a much smaller search space in trying to correlate our landmarks within a smaller area. And each cycle, using this technique, we're actually resetting our odometry relative to our rangefinder estimated position. So we don't get that accumulated error that we would if we were just using odometry for all our navigation that we looked at previously in some of the very early lectures. So what are the main elements of SLAM then? We've got these main elements here, and we'll discuss them in a little bit of detail. We need to extract landmarks, we need to perform data association, we need to perform status estimation, status updates, and finally landmark updates. So firstly, we have the aspect of landmark estimation. Basically, we want to look for features that we can easily reobserve, that can be distinguished from each other, so we don't confuse them with each other and try and associate ourselves with a wrong landmark. They should also be stationary. There's no point having a landmark that's actually going to take off and move through the environment with us. And there should be lots of them as well, so they should be plentiful. So we don't want to just base our estimation of a couple of landmarks like we were doing previously. We want to base it off lots, and the more the merrier often. These characteristic objects or these characteristic landmarks will help a robot localize itself within its environment. And you can imagine these a bit as if you were walking blindfolded, the sort of simple landmarks, or trying to walk around, stumble around at night in your house, the sort of landmarks that you look for. Things like maybe the door frame as you're feeling out, or the doorknobs, or the railing on the stairs, or each step as you're walking along them, you count them up. The various furniture, this is where the couch normally is, and those sort of things. And they're great until someone moves the landmarks. Someone moves the couch and you end up walking straight into it, rather than using it as a landmark to guide you past it. So we want to have landmarks, primarily the static landmarks that aren't going to be moving within our environment. So we have a sample room here. This is what one of our labs used to look like before some of the renovations that were performed in 2016. And here we see quite a few good landmarks there, but probably a few bad landmarks that could come up as well. So some of the good landmarks are things like corners and straight lines with all those cupboards and doors and things like that. The corners that form around the door there help us distinguish one door from the other door because one goes in and one doesn't go in. And there's some other obstacles in there, like the chairs there, or the table legs and things. The table legs are pretty well fixed, and so they're not going to move. And we've got some tables just off to the side of these that we can't actually see in the frame. The chairs, though, it's probably a pretty dumb spot for the chairs because people walk through the door and walk straight into them. So they will move. Someone will move them very soon. And so they're not such great landmarks if they're going to be moving. However, if they're fixed, particularly if they're bolted to the floor or something like that, they could make very good landmarks. So how do we actually extract landmarks? Well, it's dependent on the type of landmark, and we've got two main ways that we do it. One is spike extraction, to look for objects with a large discontinuity. For example, the table or chair legs or poles and things like that. And then we have ransack, where we're looking for straight lines. And we looked at ransack in one of the earlier machine vision lectures, so we won't go into detail about ransack now. But the spike estimation, here we're looking at, for example, a laser scan, where we're looking at adjoining points where we've got a significant threshold. For example, maybe a 30 centimeter distance from one point or a couple of points that have been measured to the background there. And we'd identify this as a spike within the environment. So for the laser scanner, laser rangefinder measurements that we've got above, we see a whole lot of dots there, and then we see a whole lot of curved lines. And so those dots might be things like chair legs or table legs that are spikes within the environment and are significantly distinct from the background area that you've got there. These can work well where we've got lots of objects in the environment, but they're not so great for a plane environment because we may not have these spikes actually occurring. The room might just be clear. And then we'd be dealing more with the ransack we've got there to localize ourselves based on the walls or flat objects within the environment. Now, our next thing that we need to do is data association. Now, after we've identified landmarks, we don't just say, hooray, we've found some landmarks. We actually need to try and match them with landmarks that we've previously identified. And unfortunately, this process can be quite difficult because we might not see a landmark all the time. Some landmarks might be landmarks that shouldn't really be landmarks at all. They're moving and things like that. Or we might not see them from a particular angle, but we can see them from a different angle, and so we might miss those sort of landmarks. And so they're temporal based on the position that we're observing them at. We might see a landmark but never see it again. Once again, a bad landmark. That we saw it at one point, but someone's moved that chair out of the room and there's no landmark there anymore. It might be difficult to, as we observe our landmarks from different positions, to actually identify them and say that's actually the same landmark, because from a different position it might look quite different. We might also associate a landmark with the wrong landmark that we've previously seen in a previous cycle. This can be a big problem and can tell our robot that we're actually in the wrong position, because it thinks it's seeing landmarks that it's matched, but it's actually seeing different landmarks. They weren't the ones. It shouldn't have matched them and associated with them with those particular landmarks. And so essentially what we have is a database with a whole bunch of landmarks associated in there. We start with an empty database unless we have prior knowledge of our environment, like we can load a map in there. And what we're looking at is not considering something as a landmark, as a good landmark, until we've seen it n number of times. So we set some sort of a threshold and we say we need to see it 10 times or 100 times or whatever it may be. Once we've seen it that many times, we're fairly confident that it's static over the time that we've actually seen it at, and we can add that to the landmark database. And this way we try and exclude some of the bad landmarks that we had where someone was walking past the robot or something like that. And our next thing that we need to do is our state estimation. This is where we use our extended Kelman filter. And essentially it's pretty simple. We're estimating our robot based on our odometry. So the sort of odometry calculations that we had in earlier on lectures, where we're computing the new X value, the new Y value, and the new theta value, the new angle. And here we're using our basic wheel and code calculations to compute the position. We've looked at this sort of thing previously. And then what we need to do is a status update. So here we update our robot position based on re-observing landmarks that we've seen previously. So for each re-observed landmark, we want to estimate our position using our current robot position. So our current robot position should get us fairly close, and then we use our save landmark positions to estimate a new position of our particular robot. And we can compare these between our previous state where we're doing our state estimation and this new state where we're updating the status of these. So we're using our extended Kelman filter and updating our new position, estimating our new position based on how we observe all the landmarks around us and how we re-observe them within the environment. Now, we won't go into detail on the maths and things in that because we haven't covered Kelman filters in much detail either. And one thing we might need to consider is updating the landmark database. If a landmark's new, for example, it's something that hasn't been re-observed because it wasn't in the database to begin with, we need to actually add it to the database, particularly if we've observed it a number of times and we're convinced that it should be added in because it's met the minimum number of observation thresholds that we've got there.